Okay, so now to the main event. I'm very excited to introduce our speaker today. We have Joe Aumentado from NIST Boulder. So for many years, he has been one of the leaders in the development of parametric amplifiers for superconducting circuits and superconducting quantum computing technologies. And he can tell you much better than I can what he actually works on. So Joe, take it away.
All right. Thank you. Thanks to Alicia and Kartik and JQI for inviting me out and hosting me. It's a pleasure to be here. I don't know which end of this thing I have out.
Directional, as long as it's about your person.
Okay. So I go by Joe. You will see on papers that I go by Jose because that's what my mom named me. But so today I'm going to tell you about this thing called the Field-Programmable Josephson amplifier. This is a new class of parametric amplifier in superconducting circuits. And it utilizes this notion of multi-mode parametric coupling, kind of beyond what we normally think about in parametric amplifiers, as you might know them today. And so I come from NIST in Boulder. Man, this pointer thing is really kind of bonkers. I come from NIST in Boulder. There are two NISTs, as many of you know. There's one in Gaithersburg nearby, and then there's one in Boulder. And I never go to the Gaithersburg one, or I don't go often enough to visit my colleagues. But we are a smaller sibling, I think, in terms of size. But we like to try to punch above our weight. So if you're in here or you're part of JQI, you probably have some sense that quantum computing is some sort of exciting endeavor. And if you read the press, you know that there's all sorts of fantastical things that you can do if you have a quantum computer. And this is all great. I'm not here to talk about any of this stuff. I'm not going to talk about computing or algorithms or anything fancy like that. What we do know is right now, superconducting circuits seem to be a very, very powerful platform that lots of very big companies are excited about and trying to build quantum computers in. So superconducting circuits are exciting, at least for this idea of doing quantum computing. There are a few things that you need. You need qubits. We all know about that. We need a way to control them, both at the single qubit level and also in terms of coupling qubits together to perform 2 qubit gates. And we need a way to read them out. Of these, and you might recognize this as like a bastardized version of the DiVincenzo criterion. But of these, the thing that we don't really talk about is this kind of readout task. And for me, this is a very big deal because we've all seen pictures like this and they look glorious. Some people will say it looks like a chandelier and somehow that's a good thing, but it looks like big science, I think, to a lot of people. And something important is happening in here, mostly because it's very shiny. There's lots of gold, lots of cables. So it must be complicated and maybe imbue some sort of importance to it. But this is a picture from IBM. It's already a few years old. This is really just a mock-up that they could afford to build for people like us to see. It really was only intended to hold something like 50 qubits, physical qubits. But to build something that's fault tolerant and can do universal quantum computation, the number that people talk about is something like 1 million. And if you look at the scale here, this is a dilution refrigerator with a mixing chamber plate about yay big. The idea of doing 1 million now starts to look really intractable, and all this cabling and all of this other stuff starts to look like a problem, right? Okay. So if you're IBM or some other large company, you have a lot of money, you can think about brute forcing the problem, just building a gigantic fridge, maybe even bigger than this one. I can't remember, I think these are like the CEOs, one of the CEOs and some chief science officer or something, sitting inside this fridge. I should know these answers, but I don't. And this might take you to something like 1,000 or 10,000, maybe even 100,000 qubits, but to get to 1 million with all that hardware that we saw, that's going to be really quite the task. So if we look very closely, we look a little bit more closely at what's going into all the stuff that you see, there's a lot of hardware resources that we don't often talk about. One is this idea of trying to get signals in and out of the system. Those are all those cables that you see going into the fridge. That's the input-output cabling. And then there's a bunch of measurement stuff. There's passive isolators and circulators and hemp amplifiers, transistor-based amplifiers you can see up here. All of this goes together to create a kind of a big footprint for measuring these devices. So apologies if things are cut off here. It wasn't cut off on my computer when I was working on it. Okay, so this idea of having a bunch of cables and having concomitant hardware to go measure a few qubits, this is okay in a demonstration sense or an artisan sense where we're trying to do small demonstrations of very simple quantum algorithms. But if you're trying to build a computer, it's kind of a disaster. So if we look at this system, again, we can go notice that the qubits, they sit in here inside this coffee can type of structure. It's a magnetic shield and some thermal shielding. But all this other stuff around it is readout hardware. It's amplifier hardware. So meaning that it's got parametric amplifiers and circulators and isolators. These all occupy a huge footprint. So when you think about the scaling problem, we have to go and reduce the size of this stuff. So, and here's another picture because I don't want to pick on IBM solely. This is from Google. Again, this looks very beautiful. They have lots of artwork, and paintings of this kind of rat's nest of cables. And if you are an experimentalist, this looks like a nightmare. This is something that you should be scared of. And again, if you look at this comes directly from the Google supremacy paper from the supplementary. You could see the readout parts over here. This is all the readout circuitry that they're using. You can see lots of passive circulators. And this little thing that with a P next to it is their parametric amplifier. So, and I'll get to that in a little bit, because whenever you use a parametric amplifier, it always requires a bunch of hardware around it in order to operate. That's a problem. So let's zoom in a little bit. This triangle that I'm drawing over here, which I'm calling the parametric amplifier, this is actually, in our case, it's going to be a circulator with a circuit attached to it on one of the ports that is read out in reflection. That's why we're using the circulator to bounce signals off of it. And so what we're going to try to do is we're going to try to replace as much of this stuff as possible with some sort of more compact superconducting circuit scheme. And we're going to do that using couple mode theory, and we're going to use that to go and build what I'm going to claim are directional parametric circulators and amplifiers. And I'll explain a little bit what that means. So before getting to that, we should talk about what the qubit readout problem looks like in superconducting quantum computing. In this particular case, we'll just talk about the transmon. This is the most popular, I would say it's the most popular superconducting qubit that these big companies are focusing on right now. There are competing qubits now that are very interesting, but we'll focus on the transmon. This you can think of as a nonlinear resonator. So this is a capacitor over here, and this thing over here, this little X, is a Josephson junction, which we should think of as a nonlinear inductor. And so if I think of that as a nonlinear inductor, where its inductance is a function, it's a nonlinear function of the current that's going through it, that's what these expansion terms are, then we can understand that the natural frequency, omega naught, is some function of the current in this in that small circuit, that small simple LC circuit. And we're going to explore this limit where the energy levels are discrete, so they're quantized, and you can think of those energy levels as corresponding to different sizes of current inside that little nonlinear circuit. So we can go back and contrast that with the simple harmonic oscillator. Here, it could be an LC resonator or a mass on a spring, and look at its energy potential. It's a quadratic potential, and as we know from undergraduate quantum mechanics, the energy levels are spaced evenly, and so we can describe that system with a single frequency, the simple harmonic oscillator or natural frequency of that linear resonator. So if we bring it up at that frequency, if we try to drive it at that frequency, it'll just climb this ladder of states and then settle into some steady state, which is determined by the dissipation rate in the system. But if we look at the transmon qubit, it has a cosine potential for its potential energy. In that case, what happens is the potential kind of softens up at the top. And what that means is that the energy levels, as you climb this ladder, they become closer and closer together. And so what we do in the transmon case is we use this fact to go and isolate this ground and excited state manifold. That energy difference between the ground and first excited state is different than the energy difference between the excited and F state. This is a choice of two modes that you can go and use. If you like, and people don't really say this enough, I think, this is the electronic analog of the pendulum, which I hope everyone remembers is actually a nonlinear oscillator itself. Okay, so to read out the state of this qubit, what we have to do is attach it to the outside world. And we do that by probing it with some microwave field. And so these red arrows are indicating a microwave field incident on the circuit, and then we measure its reflected response. But we do something special, which is to go and hide the transmon behind a linear readout resonator. And that linear readout resonator acts as like a filter, meaning that if I was a transmon and I'm looking out in the environment, this resonator actually filters what I see from the environment. And so if these qubit and readout resonators are detuned by, say, like a gigahertz, then this transmon is actually kind of hidden from fluctuations in the environment at its frequency. And so the way readout works is as follows. The two states of the transmon correspond to two natural frequencies of this linear readout resonator. And what they do is they load this linear resonator in such a way that if I was to go and ask this linear resonator, what's your resonant frequency, it actually shifts it left and right, depending on whether this is in the ground or first excited state. So you can imagine if I sit here and I measure the reflected response at a fixed frequency, say 6 gigahertz, I'll see two different phases in the response. And so if you like, and maybe this is useful for some people, I don't know, you can imagine that the two states of this electronic pendulum maybe has a small oscillation mode and then a big oscillation mode. Those two things act to go and shift the phase of the oscillations of the linear harmonic oscillator mode. So if you can read out the phase of the oscillations in the linear harmonic oscillator mode, you can read out the state of the qubit. And you know, in the jargon of the community, we say that this is a QND, or quantum non-demolition measurement of the transmon itself. So our goal is to measure this qubit state by measuring this qubit state-dependent frequency shift. And we want to measure it as fast as possible, faster than the decay rate of the qubit itself. And I haven't talked about the decay rate of the qubit, but these qubits have a finite lifetime, and so you need to go and assess its state before it dies. And we want to do this at very low power, meaning that we have to stay in this limit. If we go to a higher power, we can start to disturb the qubit and start to dephase it in a way that's really bad for our purposes. So you can imagine, okay, looking left to right, and going to kind of a phasor representation of the signal that we're injecting. Here, I'm plotting that signal in this, what they call the IQ plane, or image quadrature plane. I send in some signal. It has some amplitude, it has some phase. It enters this linear readout resonator. It interacts with a qubit in some way, and it acts to phase shift these two blobs in the IQ plane. So the one blob corresponds to the ground state, one blob will correspond to the excited state. And our goal is to go and read out that phase shift in the IQ plane as fast as possible. Okay, and there are lots of ways that people can configure to do this. I have an example. This is taken from a review article written by the Google guys in IEEE Microwave Magazine. These are coplanar waveguide resonators with quarter wave resonators attached to transmons, these X-shaped objects. The thing that maybe you might be familiar with is the case of the 3D cavity of the 3D transmon, where you have a transmon circuit placed in a 3D resonator. You could read it in transmission or reflection. And again, you're reading out some phase shift that corresponds to the state information. This figure is actually taken from the original 3D transmod paper, if you haven't read it. Okay, so there are other requirements that we need, which I'll just rush through quickly. All these circuits, they're made in aluminum or iodine. We have to be much colder than the superconducting transition temperature, which for aluminum is about 1.2 Kelvin. Fine. But we also have to be much colder than the thermal background, which is dictated by KT here. Basically, we want KT to be much smaller than the frequency of these circuits, the natural frequencies of these circuits. And so if we're talking about something like 10 gigahertz or so, we want to be much lower than a half a Kelvin. In our case, we can get pretty low. We can get down to around 20 millikelvin in a normal dilution refrigerator, the way these things are built. The other thing that you need are amplifiers to go and read out the state, because we're using very, very small signals. We need to go and amplify those to get more signal, hopefully with not a lot of noise, preserving the signal noise ratio. I'll talk about that. So the kind of workhorse amplifier that everybody has in their fridge is this thing called the HEMT amplifier. It's a high electron mobility transistor. It's a solid state based amplifier. These things typically have something like 40 dB of gain, but they also have a lot of noise. Here I'm talking about it in terms of noise temperature, and I'll say a little bit about that in the next slide. But this noise is really not great. And you might wonder why, like, we've placed it up at a higher temperature stage. That's because they dissipate a lot of heat. So in a practical sense, they're kind of a disaster for measuring quantum circuits, because you can't place them close to the device you're measuring, because I don't know if everyone knows, but in a dilution refrigerator, at 20 millikelvin at the mixing chamber plate, you just don't have enough cooling power to support something like a HEMT amplifier and its power dissipation. So it dissipates a lot of heat, and it's also pretty noisy. Yeah.
If you could, would it make a big difference?
So it can, and that has to do with the fact that you can reduce some of the components, the intervening components between the readout resonator and the amplifier, and that reduces loss. And those components can be cold, so they don't introduce a lot of added noise in the measurement itself. It's a little bit of a technical detail. Like, it would be fine if this device, if this amplifier dissipated a lot of heat, and I could put it up here, and it had really good noise, which it's okay, but it's not super. And then you had no loss between the resonator and the amplifier. But the fact of the matter is, all these components that we add, connectors and extra cables and things like that, introduce some loss, and that kind of kills the efficiency of the measurement in a particular way. But it's a little bit more of a detail that I can talk about later if you're interested.
Could you say just a little bit about the isolator and what?
Yeah, so I'll often show things like isolators and circulators in this talk. These devices, they're usually passive devices that are based on ferrites, and so the idea is that they're magnetically biased, and you have maybe the isolator is especially simple. So you have some transmission line with kind of a funny structure, but it's just built on a slab of ferrite. It can transmit in one direction, but then the idea is in the other direction, it goes and isolates, it dumps the power into some load inside the device.
That's just the same thing we would use at room temperature.
Yeah, exactly the same thing. So
century.
That's exactly right. So it's very old technology. We're more familiar with circulators and isolators at room temperature. For cryogenic use, we use slightly different ferrites, just because they're better performing at lower temperatures. One of the important things about circulators and isolators is that they always have some insertion loss, some loss that comes along with it. It's something to do with the physics of ferrite materials that I don't really quite understand. And so whenever we talk about using an isolator or circulator, it always incurs some loss in your signal path, right? Sometimes it matters, sometimes it doesn't. If it's before your first stage amplifier, then it's always going to incur some penalty.
But that also means noise.
Yes, that's right. That means noise. So I don't have the slide here, but there's kind of a beam splitter model for loss that you can use to think about how you add noise into that. And I think I have a slide on this, which we'll talk about in a second. So the hemp by itself it's not a great amplifier. I mean, it's a great amplifier actually. It's super wideband, has a lot of gain, it's pretty low noise, but we need to do better. And so what people do is they add in this paramp. I call it a paramp. It's a parametric amplifier, and for short we call it paramp often. This is a preamplifier, which is super low noise. It can't handle a lot of power most of the time. But in terms of noise performance, it's pretty awesome. And so let's talk about that. So remember, our job is to go and assess the qubit state by distinguishing two blobs in the IQ plane. If we can average for a long time, we just average forever, and then we can go average away all the noise, and you get really distinct points in the IQ plane. That's great. But we don't have it forever because the qubit's dying as we're trying to measure it. So we want to measure it fast. And so if I was to go and listen right at the output of the readout cavity, I might see something like this. Those are the two blobs that distinguish the ground at first excited state, but they're fuzzed out a little bit, and that fuzz corresponds to 0-point fluctuations in the electromagnetic field. That would be great if I can go measure that directly, but I can't. The signal's too small, and I have to go send it up through this chain and amplify it so that I can go and demodulate it on receiver hardware that actually can go and distinguish these two states in my instrumentation. And so that's kind of a tough issue, but the reason why is that any sort of amplification chain that I introduce into the system is going to add noise. And specifically, I mean, we could write it in this sense, right? If I take the power out of the system, the signal power out after it's amplified, there's some gain factor in front. We have the signal, but then we have some uncorrelated noise that adds on top of that. Often, you know, if you think about low noise receivers at all, you might characterize this in terms of the noise temperature in Kelvin units, but more often than not in these ultra low noise amplifiers, we talk about this thing called the noise number, which I'll call N sub n, and that is just normalizing that noise temperature to single photon energy. And so if you're doing everything correctly, you know, if you have this ideal, so let me go through this a little bit, these numbers. So if you take a typical hemp amplifier, your system noise with this amplifier installed is typically on the order of a few tens of noise photons. So when we talk about noise number, we'll often say noise photons. It's just jargon. And if I was to go look at the IQ plane, we can see that it would basically fuzz out that ground at first, those first excited state blobs rather significantly. So the job of distinguishing between ground and first excited state is now obfuscated by all of the noise that we've introduced in the system just by using this amplifier to boost the signal. Ideally, if I have linear phase preserving amplifier, there is a minimum amount of noise that quantum mechanics demands you should add, and that is, in these units, half a photon of noise. So this is something that we call the standard quantum limit for linear phase preserving measurement. If we were to have a linear phase preserving amplifier, those blobs will get fuzzed out a little bit, but not a lot, meaning that you can still freely distinguish between the ground and first excited states pretty easily. If you had an amplifier that really performed with this noise performance.
But you're supposed to be amplifying just one photon in your system, right?
No, I mean, like here we're sending a coherent state into the system, it's interacting, and now we're just trying to distinguish coherent state phases.
Okay, so it's not the one photon in the qubit, it's your, okay.
Yeah. So, okay, so the other thing is, I mean, I don't know if it's obvious to anybody. I wrote it here at the bottom. These I and Q plots are reference to the amplifier input, which means we're dividing up the gain. Often when people talk about the amplifiers, they'll brag about, I got 30 dB of gain or 40 dB of gain. It really doesn't matter. What really matters in the end is like after I go and divide out by the gain, we call that referencing to the input, that the noise is actually minimal. I've added minimal noise to the entire amplification process. If anyone has any questions about that, I can answer that later. So with a typical parametric amplifier, we're numbers for the noise number are really on the order of 2 to 4 times the standard quantum limit. So 1 to 2 added noise photons, and that's a pretty good performance in the scope of things. So
you're going to get to this
Yep.
on the next slide or so.
Yeah.
But when you say you have to add noise, I mean, that's true for a certain class of amplifiers that are not phase sensitive.
That's right.
And so are we going to go there?
So not in this talk, or I have it on my other computer. I mean, this is just what I have within this slide deck. But the what you're getting at is phase sensitive amplification. There's no quantum limit in that sense. So right, it's for one quadrature. So I have to pick a quadrature. And this is a really great way to go if you're only measuring one qubit. So ultimately, you might be trying to measure 5 or 10 or 100 qubits with a one amplifier, in which case they're all going to live at different frequencies. The readout frequency is going to live at different places. As I try to do phase sensitive readout and all those simultaneously is I don't want to say it's impossible, but like it complicates the problem a lot. So the easiest kind of baseline thing you can do is this phase preserving linear amplification. But yes, you are correct. That is a very important point. If you want to know more about readout, there's this kind of fantastic paper by Andreas Wallraff's group, which I can refer to here, that talks about some of these problems in readout. Okay, so one of the things I mentioned, or that Alan asked about, was or alluded to, was this idea of loss, or maybe it was Bill that referred to it. That if you have loss in front of your amplifier, it has the effect of actually, you can go and cast it as like an effective amplifier with less gain, but then you actually increase the added noise of that system in some fundamental way. And so I apologize, I think some of the grid lines are not showing up here, but you'll have to imagine that this grid lines on this plot. Here, this n sub n prime is the effective noise of this total loss plus amplifier circuit. What you can see is that it's basically going up as I add more loss to the system. So if I have an attenuator that's 3 dB, then I have more than doubled its added noise. And so the idea of adding loss in front of your device, or in front of your amplifier, is really, really bad. And so where's that loss come from? It's all the extra stuff we need to actually operate a parametric amplifier. So there's bias tees, connectors, there's couplers, there's extra circulators and isolators. All of this is a bad thing. And so what we're trying to do is remove all of those components, as many of those components as possible. And it has the added benefit of reducing the physical footprint of the amplifier itself. Okay, so and this is just a little mini rant. Most amplifier, if you read the literature and you read about people's parametric amplifiers, they always say that they're awesome, they're quantum limited. That's really not true, because you need a bunch of stuff to operate the amplifier. And so if you go and you look at the total chain, including that loss in front of the amplifier that you actually need to operate the system, things are not quantum limited anymore. And that's okay. It's, I mean, it's not okay. It's just, we have to be okay with saying we're not quantum limited. I think it's a weird bias in the literature for some reason. This is what I was talking about before. You need this thing that we're saying is quantum limited is the JPA. Maybe it's a chip itself, but you have to put it inside a package, and then you have to go and add other hardware to go and read it, and all that stuff is going to add to go and detract from the noise performance. And so this was just a slide to show you what these circulators look like. It is really a few centimeters in scale. You saw them on the previous pictures for the IBM and Google systems. The other thing that we don't really talk about is the fact that they have permanent magnets inside, and so you have to shield these really carefully if you're going to try to put them near your superconducting stuff. And so all that extra shielding also takes up space as well. And having big magnetic fields near your superconductors is just in general a bad idea, not an ideal thing to do. So, okay, that was a picture to show you all the ferrite circulators. So what we're going to try to do, and to fix all this stuff, is reinvent parametric amplification a little bit. And so to understand what we're going to do, it helps to understand basics, the very basics of parametric amplification. And so it all starts with the linear harmonic oscillator, or the simple harmonic oscillator. And let's go through its cycle of oscillation, right? If I load it up with charge up the capacitor plates in that LC circuit, we know that over time it will discharge and turn all of that electrical energy into magnetic energy in the inductor, right? It'll turn into magnetic flux inside this inductor. And then the process will reverse. It will charge the opposite with the opposite sign and then drive the magnetic field in the opposite direction inside that inductor. This is a cycle. This is the oscillation cycle. It's not very mysterious. But if you want to say you're doing amplification, you have a couple of options. And it ends up being really simple. Basically, you modulate one of the reactances, either the capacitance or the inductance, and you modulate at exactly the right point in time. And what is that right point in time? It's really when that element is holding all the energy. And so in this case, if we want to amplify by modulating the inductance, we just wait until it's all the energy is in the inductive term or the magnetic energy term. And so if we increase the inductance at these particular moments in time, then we can go and inject energy in the system. That's the process of amplification. And so this is, you'll notice that this happens twice a cycle. That's where this notion of pumping at twice the frequency or modulating at twice the natural frequency comes from, that you might be familiar with. That's because there's two parts in the cycle where you can go and inject energy. And so when people talk about so-called JPAs or Josephson parametric amplifiers or flexion parametric amplifiers, really what they're mostly talking about is this very simple circuit. It's just an LC circuit where we modulate its inductance at about twice the natural frequency, and we just measure in reflection. So I send in some signal at F sub S, and then it gets reflected out, amplified at F sub S, and then there's an additional signal called the idler, which is at F sub I. And so it might help to think about this as a mixing process where this modulation process, it's like that pump frequency can be considered an LO or local oscillator frequency. And then it generates this sideband, which is the idler frequency, which is actually counter-rotating. It's rotating at a negative frequency with respect to the signal frequency. I like to show this diagrammatically. So if I show the density of states available to the inductor, you imagine you have some signal frequency here, and then you have some pump frequency or LO that's mixing it to this lower sideband over here, which you can see is counter-rotating. It's crossing zero. Every time you have a mixing process where you mix from a positive and negative frequency or vice versa, that means that you're injecting energy in the system. And that means amplification is happening. Okay. So the other important things you need to know is that these signal and idler modes, these frequencies have to live within a line width of the natural frequency. And I said this bottom part here, the positive and negative frequencies, mixing between positive and negative frequencies corresponds to amplification. You can calculate the scattering parameters. Here's the reflection gain from this amplifier. As I increase the pump power or the modulation amplitude, I can get more and more gain up to some critical pump power, which I won't talk about here. Crucially, you might also notice that the bandwidth decreases with a gain. This is a feature of a lot of parametric amplifiers. It's not like fundamental, but it is for these, what I would call single pole parametric amplifiers. One of the things that Bill was alluding to earlier was this idea that phase preserving versus phase sensitive. You get phase sensitive gain when the pump is exactly twice the signal frequency. Here we're always talking about the limit where it's not really a limit, but we're always talking about the case where the signal frequency is detuned from the half pump frequency. So we're always talking about what we call phase preserving gain, which means it amplifies both quadratures, any quadrature equally. It doesn't matter what the phase of the signal is coming in, it's going to amplify it the same way.
So did your cartoon picture sort of assume that you were frequency locked, right? Sometimes, or maybe not, because it seemed like you were modulating each time you were at a peak.
That's right. So there's some sort of phase coherence as part of the picture. It's actually not as important in this case in the phase insensitive or phase preserving mode of operation, unless you're trying, unless like I shouldn't say that. It's a little bit more complicated. So there is some sense of being phase sensitive. It's not in the same way that you are in like the phase sensitive case where you're pumping at twice the signal frequency. So so you actually have some latitude. You can have some noise in the pump phase and it's not going to kill you. But it's a little bit more of a deeper question. So when people talk about degenerate parametric amplifiers, we're really these are amplifiers that are measured in reflection. They're sometimes called negative resistance parametric amplifiers, and they need some sort of circulator to go and separate input from output on different physical ports to give it an actual input port and an output port. And we've referred to this
on the web.
Siri. And we refer to this idea that they can be phase preserving and phase sensitive depending on how we choose to operate it. There's a more general version of parametric amplification, which I'll call non-degenerate amplification. Well, it's called non-degenerate amplification. There's a little bit of a jargon here. If we look at this toy circuit here, we can see that there's two dominant modes here. There's actually a common mode, which I'm not talking about here, like a loop mode that bypasses this. But if we look at these two inductors here, or sorry, these two meshes here, imagine two mesh currents, and they both share a common inductance branch. That's this red inductor over here with the arrow. This is the thing that we can parametrically modulate. If we take these two tank circuits and think about that mixing picture again, you can see that basically, of course, amplification still happens, except we're pumping at the sum of the two resonant frequencies. And what that does is it connects current circulating in one mode with current circulating in another mode at a negative frequency. So it's the same kind of mixing process that we saw before, but it's a little bit more general as it traverses different resonant circuits. And as before, you can go and calculate the gain in this circuit. It basically has gain and reflection at both ports, but then also has this frequency converting type of gain, which is sometimes called trans gain in the literature. So it has gain basically all different ways, cut it. And like before, the bandwidth still decreases as you increase the gain. Okay, so just a note about jargon. When people talk about degenerate versus non-degenerate parametric amplification, what they're really saying is that the signal either frequencies either live within one tank circuit or they live in two different resonances of the same circuit. So this, apologies, some of the text has gotten misaligned, but anyways, there's an important counterpart to amplification. That's straight up frequency conversion. This is where we modulate the inductance of the difference frequency between two different resonances. And again, in that kind of density of states picture, you can see that mixing process really just connects the two resonants rather directly on the same side of zero. So positive to positive and negative to negative. And again, we can compute the scattering parameters just like we did before. This is actually really important. It's one of the tools that we're going to talk about in our tool set. You might be concerned that I haven't talked about quantum mechanics at all, but it's kind of okay because we don't need to talk about quantum mechanics when we're talking about amplifiers. All this stuff works at room temperature, works at low temperatures, whatever. The basic process for amplification doesn't require quantum mechanics. But if you want to connect it with what you already know, you can just go and write down. You can just look at this circuit where I imagine I have two mode currents oscillating at different frequencies, and they're going through the same shared inductance branch, and I'm allowed to go and modulate that inductance branch like so. And here I'm doing it sinusoidally. And if I write down a Hamiltonian for that magnetic energy term, I can break it up into its annihilation creation operators, and I can get all the stuff that I'm familiar with. Single mode squeezing. This is close to the degenerate parametric amplification case that I talked about before. Dual mode squeezing, which is this non-degenerate mode of the amplification that I talked about as well, and then frequency conversion. And so you might recognize this as a beam splitter Hamiltonian, for instance, if you are into quantum optics. So anyways, what I'm doing is I'm choosing a completely classical description of everything, but if you want to be quantum and talk about quantum mechanics, we can do that too. I think it obfuscates the general operation and what we're trying to accomplish here, especially when it comes to non-reciprocity, which I'll talk about in a bit. Okay, the other thing I'm going to kind of gloss over is what we use for these modulated inductors. If you know about superconductivity, you know about squids, we're going to use a DC squid. We often use DC squids to go and create this nonlinear inductance modulation. If anyone has any questions about this later, I'm happy to go and talk about how that works, but we won't do that for now. So we'll skip over that. And Next. Okay. So now we're finally gonna state the problem. I'm 45 minutes into this talk, I think. What I want is I want a parametric amplifier because it's low noise. I haven't really talked about the noise properties. We want it to be directional without adding circulators, without physical circulators, and I want it to be small, compact. And we have this general prescription for parametric coupling, which includes amplification and frequency conversion. Already talked about. And if we choose, we can go and write this in a scattering description where I have a set of input fields and I have a set of output fields, and they're connected via this scattering matrix shown here. So let's take these pieces and we'll try to talk about reciprocity. So reciprocity is this invariance with respect to the exchange of the source and the receiver. It means that it doesn't matter if I put the source on this side, the detector on this side, or the source on this side, the detector on this side. We are invariant to that placement. And so a way of saying this in terms of scattering parameters is saying a system is non-reciprocal if S21 is different than S12. Those are the matrix elements that connect the left to the right and right to the left. So if you've read POSAR or familiar with scattering matrices in some other context, you know about this idea of non-reciprocity, and this is how they talk about circulators and things like that. But this doesn't work if the two frequencies are driven at if the two ports are driven at different frequencies. And so there's a more general constraint, which is that the transmission from one frequency to another versus from left to right versus right to left, it has to be different up to some arbitrary phase shift. And this is this kind of gauge invariant condition you might see sometimes in the literature when they're talking about non-reciprocity. So and so there's this kind of there's this more general condition in a multi-port system where you have a lot of driven signals and you're trying to ask, is the system non-reciprocal or not? So I won't talk very much about this, but it is important in understanding our case where we're talking about parametric frequency conversion amplification, which is fundamentally a frequency translating process for both things. So so one of the things that's important is that if you only have two modes, amplification and frequency conversion processes are not directional. They're cool, but they're not directional. And so what you need is a third mode. And the idea is that we're going to go and combine multiple amplification and frequency conversion processes to produce directionality in this circuit, which means scattering from one frequency to another in a directional way. Yes?
On your previous slide, I'm a bit confused. You mentioned that scattering amplitudes have to be different up to some phase. So what's the distinction between that and just being different from one another?
So just being different. So you can transmit through a circuit and some amplitude, and it scatters and its amplitude changes going in the forward direction, and then you could have that same amplitude go, that same reduction or amplification happen in the other direction, and they might be different by a phase shift, right? So that's what we call gyrational coupling. So you have a difference in phase shift going in one direction versus the other. That's a form of non-reciprocity, but a more general condition is that in this case where you have two different frequencies, say I come in at 6 gigahertz and I go to 9 gigahertz, or I inject at 9 gigahertz from the opposite end and come out at 6 gigahertz the other end. There's an ambiguity about the frame of reference that you're talking about the phase shift in, and that's what this kind of more general condition is talking about. And so in cases where you have frequency translation or a shift in frequency, there's kind of an ambiguity about what the appropriate frame is to talk about those two things. I can imagine a beat note, maybe if I just directly mix those two things, and that beat note can kind of live anywhere in time, and I have no reference for it, the relative phase between these two signals. And so that might not answer your question. It's a little bit more in the weeds, but the idea is that there's no general reference frame for these two frequencies, signals at two different frequencies in which to talk about whether something's non-reciprocal or not. Realize that might not answer your question, but I can talk about it later, maybe, if you're interested. So, okay. The general notion here is that we're going to use 3 or more modes, and in that case, we'll have the appropriate ingredients to go and make something non-reciprocal. And so we're going to add more circuits here. And so you can imagine loading it with more tank circuits, and then using this kind of common modulated inductance to go and do frequency conversion or amplification between different resonant circuits. So you can imagine, say, driving coupling between 2 of those circuits, A and B, maybe driving another, pumping at another frequency and driving coupling between A and C, or any other combination. But there's nothing to stop you from driving multiple couplings simultaneously, or coupling them into loops, for instance. And so the idea of in our group of multimode parametric coupling is to go and couple things in maybe lowest order non-trivial topologies like loops. And it's going to be especially important to talk about non-reciprocity. So I'm going to gloss through this, but like I'm going to use this graph picture over and over again. I just want to show you really where it comes from. I can write the equations of motion for the complex mode amplitudes and all those tank circuits, all those LC resonators, and they're going to have some coupling terms that are generated via the parametric coupling. And what we do is we Fourier transform them and then into the frequency basis, and then when I talk about M as being the Fourier transform equations of motion, that's what that means. I've Fourier transformed this whole thing, and then I can go and relate it to a set of input fields that I'm driving the system with. And so you can use the input-output relations, some generalized form of that, and then compute a scattering matrix from that boundary condition. And so when we talk about, this matrix M, it's really the way that all the different modes or all the different frequencies are connected together parametrically, and from that we can derive a scattering matrix in some simple form. And so what we like to do is we like to cast all these equations of motion as a graph. So if we're talking about a single resonator, we can talk about it as a single bubble with an arrow pointing to itself. We want to talk about frequency conversion. It's 2 bubbles, a signal in either bubble. They're connected to each other. This is a way of writing the couple mode equations in a graphical form. And so let's see what we have here. So all these things have different properties. What I'm not saying, or what I'm not going to go into in detail, is that these can be used to calculate the scattering matrices directly. And it's a way to correlate the topology, the way things are connected to the kind of behaviors that are imbued by that topology. And so we have 2 fundamental ways to couple modes. It's the frequency converter and the amplifier graph, as shown here. These are ways of writing equations of motion. If you want to calculate scattering parameters, there's a procedure just by pulling apart these graphs and following certain rules to go and write down the scattering elements really directly and completely graphically. And so this is my daughter. I think she was 9 or 10 at the time. I was showing her how to calculate the determinant of this equation of motion. All this is to indicate that it's really a procedure. That's, just you can go and write out the determinant graphically if you like. It's kind of cool. It's really not very useful if you have 10 or more modes, but it's kind of cool that you can go and I never learned how to compute determinants, for instance, graphically, but she did. I don't know if she knows that she did, but she's 17 now, but it was a little bit of a test. If you're interested in any of this graph stuff, we did write a paper. It's in the New Journal of Physics in 2015, but this is really about where non-reciprocity comes from in a minimal coupled mode system. Okay, so we're going to use these graphs as a pictorial tool to kind of talk about how things are connected. I'll be a little bit more specific about what that means in a little bit. So what we found in this paper is that there are 2 very minimal ways to connect things parametrically to get non-reciprocity or directionality in a scattering matrix. That is this thing that we call the delta circulator and this thing we call the delta amplifier. And its names indicate they perform circulation and amplification. And I'll show you how that works in a second. So we're going to do that by building a 3-resonator circuit. So this 3-resonator circuit, it's super simple. We just have enough inductors and capacitors to form 3 distinct resonant modes in a system. All of them are dependent on, all the modes have a shared current branch, which is here shown as a squid, DC squid. You should think of this as just a tunable inductor. What we're going to do is we're going to put 2 physical ports on it. One's just for signal input and output, and then one is for the pump. This is the thing that will modulate the squid inductance. And again, I'm not telling you how this squid acts as an inductor, but the idea is that this is a modulated inductor, and here's my knob for tuning that inductance. We made this device using this niobium trilayer process. This is more for the experts. I'm happy to talk about this, but in detail if you want. But we're doing this we're realizing all these elements as lumped elements in the fabrication. So we're using a lot of overlap capacitors, and we're using a multi-layer junction fabrication in order to build the squid device. So let's see, there's a zoom in over there. This is a squid. It's a kind of funny looking squid. Again, I'm happy to talk about this if anyone knows about squids and wants to know more about why this is built this way. This is kind of an unusual squid. But if you look, all these elements are here. There's overlap capacitors here, 1, 2, 3, and then there's lumped element and spiral inductors here and here. And here's that third inductor, which is the squid that we're going to modulate. This is what it looks like packaged in a box. It's got a lid, but we took the lid off so you can see the chip and it launches. These are SMA connectors, if you know how big those are. And the idea is that those 2 ports are just to drive the inductance modulation, so this flux pump, and to go and access these 3 frequencies, these 3 resonances that we're going to try to couple together. And so, let's see. Okay, so when we probe this, what I'm showing here on the right is the group delay as measured from this port over here. And what I'm doing on the x-axis is I'm modulating the bias on the squid flux. So that's going to tune the inductance. You can imagine the x-axis is tuning the inductance. So what you see is that you see 3 distinct resonances at any choice of flux bias. And those are going to be the 3 resonances that we're going to couple together. They're going to host the 3 modes. And here's a better picture of it. This is the 3. Too far. These are the 3 natural frequencies, the 3 resonant frequencies of this circuit as a function of the flux bias. And what we're going to do is we're going to plant ourselves at a fixed flux bias over here. That's going to fix the mode frequencies that we're going to couple together. Those are shown here. So 4, 5.8, and 7.9 gigahertz. And we're going to try to couple energy between these 3 modes and do fancy stuff. So the first thing you can check is that you kick the tires and you see if the basic things work, like the frequency conversion I told you about earlier and the application I told you about earlier. So frequency conversion, we're just going to say, so we could couple any kind of like pair of modes in this case, A and B, B and C, or A and C if we choose to. And just by driving the difference frequency between those 2 modes. Here, just as an example, we're driving the difference frequency between these A and B frequencies, and we can measure the scattering behavior around those 2 frequencies. And so this is technically a 2-port measurement in the sense that the 2 ports are 2 different frequencies. And so we're measuring same frequency scattering. So we're injecting at some frequency and measuring that frequency, and then we're injecting at a frequency and then measuring where it comes out the other end at a different frequency. So these off-diagonal elements are basically what we would say the transmission from one frequency to another, and these diagonal elements are the same frequency scattering. And what you can see is that I can send energy in at some frequency. It completely disappears because it doesn't get reflected back out, minus 30 dB or so. And almost all of it emerges at the other end at another frequency with unity gain. And so this is the characteristic of a really good frequency converter. And when we do the analysis, so this is like on resonance what the scattering matrix should look like. When we do the analysis, we lose maybe a half dB in the transmission from one frequency to another. And we have very good match, impedance match at either end. You could also do that non-degenerate amplification mode that I talked about earlier. Remember, that's pumping the sum frequency between these two resonances. And there we see gain basically in all directions. So we see reflection gain at the A frequency, reflection gain at the B frequency, and then we see this what they call trans gain going, meaning that if I inject energy from one frequency, it gets frequency translated and amplified as well. And so both of these kind of fundamental processes, the frequency converter, the two-mode frequency converter, the two-mode parametric amplification or non-degenerate amplification processes seem to work pretty well, basically textbook. And so now what we're going to do is we're going to try to combine all these processes and do basically drive pairs of these processes simultaneously. And so in this case, we're driving our frequency converter between two modes, another frequency converter between those two modes, another frequency converter between these two modes. It forms a triangle in this kind of abstract graph representation. And so we're just doing that again by driving the difference frequency between all those different resonances simultaneously, modulating that shared inductance branch. One thing I didn't really talk about is the mechanism of non-reciprocity. Basically, a frequency conversion process is what they call gyrational, meaning that when I go and inject energy from one mode to another versus vice versa, they accumulate a different phase shift in both those scattering directions. And then what we use is this loop structure over here, bypass loop, to go and interfere that in the two directions. And so when you have gyration, you have interference, and you can get non-reciprocal scattering. And so this comes from our paper that I talked about earlier from 2015 that shows you how those different interference paths work. When you calculate scattering matrices, they can be represented graphically. And then the idea is that you can see the gyration from the different elements that are happening here. So if you know about like this, how circulators are constructed via gyrators, this all makes some sense. And I'm happy to talk about that later if anyone is interested. But that's a little bit of a technical detail. Yep.
We're getting 2 hours.
Oh, yeah, I'm going to wrap it up. Okay, so here we go. Let's make a circulator. So what we're going to do is drive all those frequency conversion elements simultaneously. I'm going to inject at some frequency over here, and you can see that basically it all gets absorbed since it has very small minus 30 dB reflection at that port, and it all comes out at another frequency with almost unity gain. And if I look at the third frequency, this frequency, nothing's coming out. At least when we're driving it on resonance. And so you can go through that exercise with all the other scattering elements in this plot and see that it realizes that, at least on resonance, a somewhat ideal circulator scattering matrix. Okay, and so if you like, this just means that when I stick power into A, it comes out of B. When I stick power into B, it comes out of C and C to A as well. Okay. Now, there's a wrinkle to this, which is that I'm picking a particular phase of the pumps to show you. But if I look at all the different phases of the pumps, I can change the direction of the circulation. And so here's the data that I showed you. What I'm doing is I'm tuning the synthesizer phase on one of frequencies, and I'm just looking at what it looks like in terms of the data, and then what I want you to communicate here is that it looks just like the theory that you would calculate here. And so what I can do is I can change the phase of one of those pumps, and I can go and easily change the orientation of the circulation. Okay, and if you like, you can think about how a regular circulator works, with 2 ferrite slabs over here on top of some type of ring or disk resonator. It's a little bit like changing the magnetic field in that case. And so often what you'll see is people talk about synthetic gauge fields or synthetic magnetic fields. That's what you're doing when you change a pump phase. Okay, so I'll try to get through this quickly. There's another case here where we drive frequency conversion, amplification, and amplification. Again, this closes a loop in frequency space, and we can measure a non-reciprocal scattering matrix. This one's special though, in that it actually gives you amplification. And so the idea here is that you know, on resonance, you kind of get this ideal scattering matrix here, where you have gain both in reflection and in transmission in certain directions. I won't go through this in detail here, but when we did this work, what we found is that when we turn this mode of operation on, it didn't shine a lot of noise back in the backward direction, and its actual noise performance, if you know about these things, is very close to the standard quantum limit, so about a factor of 2 from the standard quantum limit. Okay, so I won't go through this, but this is just to say that that loop phase dependence, the analog of what I showed you for circulation, is similarly agrees, although it has some funny stuff in the middle here, which I can talk about if anyone wants to know. Okay, so one thing to think about is like, you know, there's 3 modes. What if I just want to view it as a 2-port? So that just means, you know, kind of blanking out one of the ports here, just ignoring it and asking what it looks like. Basically, if I have a 0 on the diagonal here, it just means that all power I send in disappears and it turns into something somewhere else. And so it means in the forward direction I see gain, but in the backward direction I don't see anything. And then at the output I see reflection gain. You can do the same thing, blanking out like another row and saying I'm only going to do amplification between A and C, and then you can see I'm impedance matched at both ports. I have forward gain and then unity, a reverse gain. So there's different ways to look at this device as a 2-port and whether it's useful or not. The thing that I think is maybe fascinating about this device is that it's completely programmable. We call this a field-programmable Josephson amplifier, which means I can drive it in several different modes. It's a frequency converter, a non-degenerate amplifier, a degenerate parametric amplifier, circulator, 3 different flavors of directional amplifier here. And then there's a bunch of other variants or permutations you can take on these modes just by programming the set of pump frequencies that you're driving the system with. So you can instantiate any of these graphs kind of dynamically in the fridge whenever you like. And so you know, what I showed you is kind of version 1. That's this thing over here. The experimental work appeared in 2017, but since then we've done different variants of this where we added the phase sensitivity and tried to explore its quantum efficiency. And then we tried to read out qubits directly with this amplifier by more closely integrating the amplifier with qubit readout, meaning that there's, in this case, there's actually no circulators or isolators between the amplifier and the 3D cavity that holds the qubit. And so I'm going to rush through this. It's over time. One of the things that we're working on right now is this idea of directly integrating these multi-mode readout ideas with 3D cavities. So if you know about transmons and 3D cavities, what we're trying to do is use one of the cavity modes as one of the modes in that triangle for doing directional amplification or circulation. And so I'll skip over all this other stuff. And I should mention that there's other kind of directional work out there. Namely, Jake Taylor has some work from a couple of years ago, just using JJs, and this is more of a passively driven system. There's also systems in quantum Hall devices, which are a little bit problematic, in my opinion, but useful in contexts where there's high magnetic fields. I'm happy to try to tell you what I know about in that case. If you're interested in any of this stuff, I did write a review just on basic parametric amplifiers in this IEEE Microwave Magazine issue, and then there's also I think I co-authored with Leonard Ronzani on circulators themselves, also in Microwave Magazine. So with that, I'm over time, so I'm going to call it there. All right. Thank you very much.
So we're over time, so maybe just a couple questions also. Could just ask them at lunch.
I could ask you at lunch, but maybe a lot of people are interested in this. Like I remember when people were first going to measure a qubit with parametric amplifier, you know, they were lumped element like these, and so the question was getting the right frequency for the qubit.
Mhm.
And you mentioned trying to couple these to cavities. You mentioned something about, you know, your optimistic or your projection about how these might distribute, or whether you'll be able to hit the frequency of the cavity.
Oh,
easily,
yeah.
things like
Okay.
that.
I didn't say it here, but I've done a lot of work on trying to understand how to build wider band parametric amplifiers, and
Okay.
something that's not just a Lorentzian response. So this is based off of filter synthesis theory and electrical engineering. So it's pretty well developed, but in the context of parametric amplifiers, it's not as well developed. So we wrote a PRX quantum tutorial that I think got published last year or year before. That's a place to look, for instance, on the techniques for doing that. In this case, you can go and tune, because it's a squid, you can go and tune the operating frequencies around, so it's not as much of a issue.
They tune
Yeah.
together, but then at least one of those will match your cavity.
That's right. That's right.
I got it.
That's right. But it's not a great way to go, think about the future in terms of doing multi-channel stuff. You really need wideband stuff, which is why people are interested in traveling wave parametric
Yeah.
amplifiers as well. So,
Thank you.
okay. Yes.
So it's pretty clear that you developed something here that's really versatile, that you can do all these different things in the field, change the effective configuration. But what I'm wondering is, in the end, does it have better quality? Does it have a better noise figure? Does it, or?
Yeah, I mean, I don't want to. I talk about it a little bit in that review article in IEEE Microwave Magazine. I think these things are valuable. Like, so there's reflection parametric amplifiers and there's traveling wave parametric amplifiers. Traveling wave parametric amplifiers in general, have wider bandwidth and can handle a lot more power. So they're really great. And so people use those as their first stage preamp all the time. Turns out reflection parametric amplifiers in general are better in terms of added noise, but they can't handle as much power, and they're usually narrow band. But we can make those wider band and still retain the noise performance. And so there's kind of a trade-off there. And what we're trying to do right now is we're trying to enhance the power handling capability of these reflection parametric amplifiers, so that they're a much better first stage amplifier. I think there's room for both of these kinds of amplifiers in the world, but they're kind of different purposes. I don't think there's a good general purpose amplifier that's super low noise for everything, can handle high power across the board and have wide bandwidth. So we have to use it in some sort of like judicious combination, I think. What I like about all this, these parametrically driven graphs, these, being able to create a different graph for a different purpose at any time, is that you can dynamically generate them. You just turn it on, and now it's a completely different device, right? Even though it's the same physical device. So that's why I like the graph stuff in general. But yeah, so you use it for routing, and you can reverse this direction instantaneously, things like that. So a lot of things are easier kind of in this system than in others, but it's complicated because you have to go and phase lock, 3 or more pump drives in some kind of thoughtful way, and that's not necessarily so simple. Yeah, I don't know if that answered your question.
Sort of.
Oh, sort of, but we can talk later. Okay.
I think we should thank Joe again, and
All right. Thank you, everybody.